Hello and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to be looking at joint random variables. By that I mean we're going to be looking at two random variables at a time and considering how they might not only behave independently of one another but also how they might behave jointly. So let me just motivate this conversation just a little bit. I'll call this an example, but it's really not an example. It's mostly just a motivation. So, for example, what if I have something that looks like this? What if I've got a linear system? Of some sort. All right? And let's pretend that this linear system might have two inputs. And let's assume that my inputs have some randomness associated with it, shown here by random variables x and y. And we'll assume that my linear system has some output z, which is a function of x and y. Okay? So we'll assume that my inputs have some randomness. Alright, and we'll remember that a function of a function is a function, and we'll also recall that a random variable is a function. So if x and y are both random variables, then z is also a random variable. Z is a random variable if x and y are random variables. And just for clarity, let me just say this is my output side. And over here are my inputs. Alright, so to fully understand the behavior of my output random variable z, I need to know some information about random variables x and y. Let me try that again. That looks like a B. To understand the behavior and by behavior I mean its mean, its variance, its normalized power, standard deviation, those kinds of things. To understand the behavior of z, we need to understand the behavior of the random inputs x and y, both individually and jointly. Alright, we need to know how random variables x and y behave in isolation from one another and how they might interact or interfere or influence one another jointly. Alright, so I understand a random variable that's a function of multiple inputs. We need to know how the input random variables might behave individually and jointly. Now, strictly speaking, we could extend this kind of conversation to multiple input type random variables and multiple outputs. We're not going to do that. For this course, we're going to consider at most two random variables which may or may not influence one another. We'll look at two random variables, how they behave individually and jointly, and at most we'll consider one output at a time. Okay? All right. To begin this conversation a little more deeply, let's talk about what we call the joint cumulative distribution function. When I say joint, some books, some people will call this bivariate. Bi meaning two, variate meaning two variables. So I will almost always use the word joint. We're looking right now at the joint cumulative distribution function. Okay? All right. And we're going to assume that my two individual random variables are x and y. Two random variables, x and y. The bivariate or joint CDF looks like this. Okay, that's what the joint CDF looks like. Remember, for a single random variable, my cumulative distribution function looked like that. We'll come back to this just in a little bit, but if I consider two random variables together, we use the word joint. If we consider a single random variable in isolation, we talk about marginal CDFs and PDFs. All right. So if we talk about two random variables together, we talk about joint CDFs and PDFs. If we talk about a single random variable in isolation, we talk about marginal CDFs and PDFs. That's important. That's an important distinction. An important distinction for us to make. In the past, when we've talked about a single random variable at a time, we didn't need to qualify that by calling it a marginal CDF or a marginal PDF. It was just the PDF or CDF because we weren't talking about more than one random variable. Now that we're talking about two random variables, we need to distinguish single variable functions like that and two variable functions like that by using the words joint and marginal. All right. So that's the definition of a joint cumulative distribution function. Let's talk about some of the properties. Before I do that, let me just sketch a little picture here of what we're talking about. If this is direction, this is my random variable x, and this is random variable y, and that point right there is x, and this point right here is y. My joint cumulative distribution function, this guy, is the probability that my random variables x and y simultaneously lie in this region. That's what that means. All right? That's what that means. Random variables x and y simultaneously fall in that region in the lower left-hand corner. Another thing I need to point out is this comma. That comma right there is a conjunction. It means the word and. All right? So my joint cumulative distribution function means that random variable capital X is less than or equal to some variable level little x, and at the same time, simultaneously, random variable y lies less than some variable level little y. Okay, let's look at the properties. There are several. The first one is that the joint cumulative distribution function Let me just write all this down, I'll discuss it. All right. Recall from our discussion of single random variables that the cumulative distribution function, the marginal cumulative distribution function evaluated at minus infinity for any random variable is exactly 0. Well, for a joint random variable, there are no possible outcomes of the chance experiment if either or both of the random variables is required to be less than or equal to minus infinity. Okay? It's 0% likely that random variable x or y, independently or jointly, will be less than or equal to minus infinity. For that reason, if I evaluate my joint cumulative distribution function by letting x equal minus infinity, or y equals minus infinity, or x and y simultaneously being minus infinity, my result is exactly 0. All right? Continuing with my properties. It's 100% likely that my two random variables considered together simultaneously will take on some value. That's what that means. If I evaluate my joint cumulative distribution function at plus infinity for x and plus infinity for y, my result has to be exactly 1. All right. Third property. If I take my joint CDF and let x equal plus infinity, I take out the variability in x, I leave only behind the variability in y, and I get my I get my marginal cumulative distribution function. All right, recall that is the probability that y is less than or equal to some unspecified level. And likewise, so what I can do is I can turn a joint cumulative distribution function into a marginal cumulative distribution function by letting one of the variables equal plus infinity. Fourth property is sort of really a combination of the first property and the second property, is that my cumulative distribution function, my joint cumulative distribution function, always lies between 0 and 1, just like marginal cumulative distribution functions. Recall for marginal cumulative distribution functions, this was also a property. Cumulative distribution functions always between 0 and 1. Fifth property is that my joint cumulative distribution function is an always non-decreasing function of both x and y. All right? It's an always non-decreasing function of both x and y. It can plateau, it can flatten out as x and y or x or y increase, but it never decreases. Okay? Just like for the marginal cumulative distribution functions. And then my sixth property, we won't encounter this too much. This is the property about continuity from the right. It's more applicable when we talk about discrete cumulative distribution functions, discrete random variables. I don't believe we're going to encounter any discrete joint random variables, but nevertheless, for purposes of completeness, let me write down this property. The joint cumulative distribution function is continuous from the right. And let me just write this down a bit more precisely. The limit as x approaches x naught from the right, that's what that plus sign means. And likewise, again, I'm not going to labor over this point any further than this, except to say that just like the marginal cumulative distribution function, the joint cumulative distribution is continuous from the right. Okay? All right. The following is not really a property in the true sense. I'll present this as an example, but it's really sort of an implicit property. It's a way of working with joint cumulative distribution functions. So the question we might ask is, how do we calculate this? Right? How do we calculate the probability that x lies within some range between x1 and x2, and at the same time, simultaneously, random variable y lies within a range y1 to y2? Remember, that is an and. That comma means a conjunction, simultaneously, at the same time. All right? So what this is asking, let me make a little sketch here. If this is the direction of random variable x and this is the direction of random variable y, let that be y1 and this be y2, this be x1, x2. What we're looking for the probability of my random variable x and y simultaneously falling within that red hatched area. That's what we're looking for. Okay? All right. So recall this. Recall back when we talked about single random variables. The probability that x fell within the range x1 to x2 is the probability that x is less than or equal to x2 minus probability that x is less than or equal to x1, and that is the cumulative distribution function evaluated at x2 minus the cumulative distribution function evaluated at x1. Okay? We saw that before when we were talking about single random variables. So we can extend that kind of notion to talk about joint, the joint probability at the top of this page. So, let's do it. My probability at the top of the page can be written as this. Oops. Okay, I can split up the probability of y lying in this range by subtracting these two probabilities. All right. I can do the same thing. I can break it up the same way for the x random variable. And this becomes that should be sub 2. All right. And minus x less than or equal to x1, comma y less than or equal to y2. So that's my these two probabilities give me that result. And continuing on, we get okay. So these two probabilities here give rise to this probability there. All right. And then to simplify this one last time, this becomes the joint cumulative distribution function evaluated at x2, y2 minus the joint CDF evaluated at x1, comma y2 minus the joint CDF evaluated at x2 and y1 plus, and that plus sign is important, the joint CDF evaluated at x1, comma y1. All right. So hopefully you can see that, let me pick a color here. This region, the region when x is less than x1 and y is less than y1, this region was subtracted off twice. Can't spell today. And so all right. Okay. So there we go. Let's do a specific example. Let's assume that my joint cumulative distribution function looks like this. That's a y. Okay, this is a joint exponential CDF. That's a joint exponential CDF, and in one dimension it might look something like this. That's sort of a 1D version of my joint CDF. That's in just X, and that's supposed to be a capital F. Okay, that's a capital F. And what I'm going to ask is, what is this probability? Okay? All right. First of all, well, let's expand this out. My probability equals the cumulative distribution function evaluated at 2, 5, that's x2 and y2, minus my cumulative distribution function evaluated at minus 10, 5, minus cumulative distribution function evaluated at 2, 3, plus cumulative distribution function at minus 10, 3. All right. Now, notice, due to the step functions in my joint cumulative distribution function, it is impossible. My joint cumulative distribution function goes to 0 if x or y is less than 0. All right, so my joint CDF is 0 if x or y is less than my joint CDF is 0 if x or y is less than or equal to 0. And this is due to the step functions in the joint CDF. Okay, so for that reason then, this is 0, and this one over here is also 0. Those two pieces of the puzzle are both exactly 0. Due to the step functions, my joint CDF is 0 when either or both of the arguments is less than 0. Okay? Continuing with the evaluation, we get 1 minus e to the minus 2 times 1 minus e to the minus 5 minus 1 minus e to the minus 2 times 1 minus e to the minus 3. This is 0.8588 minus 0.8216, and that's 0.0372. Okay? 3.72%. Hang on to that. We're going to come back and calculate that same probability by looking at the joint PDF in just a few minutes. Okay? All right? All right. So enough about the joint cumulative distribution function. Let's talk about the joint probability density function. And once again, it could be known as the bivariate PDF joint, or also known as bivariate probability density function. I will almost always talk about joint PDFs. Some books, some people will talk about bivariate PDFs. It's very similar to the properties for marginal probability density functions. As a matter of fact, it's calculated by just taking some first derivatives. Okay? And remember, when we were talking about single random variables, the probability density function was that. If I have this is a marginal that's a marginal probability density function. When we're talking about a single random variable, we talk about marginal PDFs and CDFs. When we talk about two random variables taken together, we have joint PDFs and CDFs. Okay? Similar to marginal PDFs, we have this. We can invert this. We can find the joint cumulative distribution function by taking some indefinite integrals. My integral from minus infinity to x, integral minus infinity to y of my joint PDF. Okay? And that is similar to what we had when we talked about marginal cumulative distribution functions in PDFs. We had the marginal cumulative distribution function for x was found by taking the indefinite integral of my marginal PDF. Okay? That's how we find the joint CDF from the joint PDF. And this is how we find the marginal CDF from the marginal PDF. Okay? Pretty much identical relationships for joint PDFs and CDFs. Okay. Let's do a little example. Earlier we had the joint exponential PDF, CDF. We had a joint exponential CDF that looks something like this. All right. And what we want to find now is the associated joint PDF. All right. Find the joint PDF. All right, I've got to take two first partial derivatives. So let's just do it. I'm going to take my derivative with respect to x first, and then I'll take my derivative with respect to y. And this will be okay. I'm going to have to take the derivative with respect to x of all of that, and to do that I'll use the chain rule. All right. So this becomes All right, that's what that becomes. You'll remember that when I take the derivative of a step function, here, when I'm using my chain rule, I get a delta function as a result. Okay? Using similar steps now, I can take the derivative with respect to y of all of that stuff right there, and my result is the following. Okay, that gets me there. Now, remember, a delta function equals 1 only at the origin. Or more generally, delta of x minus x naught equals 1 only when x equals x naught. When the argument of my delta function equals 0, then my delta function is 1. It's 0 elsewhere. Okay? So, let's look at that thing. This piece that I've just underlined in red only exists where y equals 0. Well, e to the minus 0 is 1, and 1 minus 1 is 0. This piece is exactly 0 everywhere. Likewise, that part is exactly 0 everywhere. And so my final result for this example is e to the minus x, e to the minus y, step function x, step function in y. I can simplify that and call that e to the minus x plus y, u of x, y. Okay? It's important now for me to introduce a new term to explain how I got from there to there. All right? Let me introduce a new word. You may or may not be familiar with it. It's called separable functions. All right. If I have a function, this is not necessarily a probability density function, it's just any function. If I have a function of two variables, and I can write this function of two variables as f1 evaluated only at x and another function evaluated another function that's a function of only of y. If I can separate the variables into two functions which multiply one another, if this function of two variables can be written as the product of functions of one variable, then f of x, y is said to be separable. Okay, said to be separable. That'll allow us to do some simplifications later on when we're talking about joint random variables. So we're going to look for separable functions. So an example of a separable function, e to the minus x plus y. Well, that can be written as e to the minus x times e to the minus y. That's separable. Turns out step functions are also separable. Step function x, y can be written as the product of a step function in x times a step function in y. Delta functions are also separable. Can be written as a delta function in x times a delta function in y. And there's lots of others. Anytime I can take a function of two variables and write that as the product of two functions of single variables, I have a separable function. All right. All right. Let's go back to that for just a second. This is my joint probability density function is a joint exponential probability density function, and it might look something like this. Let's just make a little sketch over here in one dimension. It's going to look something like that. Right? That's what that looks like. Okay. Let's talk about the general properties of the joint probability density function. Properties of my joint probability density function. Very similar, once again, to properties of marginal probability density functions. The first one is the volume under my joint probability density function is unity. The area under a marginal probability density function is unity. Now we're talking about volume. 2. Since the cumulative distribution function, since the joint cumulative distribution function is an always non-decreasing function of both x and y, that means that my joint probability density function is always greater than or equal to 0. It's always positive. All right. A third and very important result, beginning with my cumulative distribution function. Remember, if I take my joint cumulative distribution function and let y equal infinity, I get a marginal cumulative distribution function back. All right? Well, from a property on a couple of slides back, my joint cumulative distribution function can be found by integrating my joint probability density function. That. So this, my joint cumulative distribution function, where my y value is evaluated at plus infinity, I can find my joint cumulative distribution function by integrating my joint probability density function, and I'm going to let that upper limit for y be plus infinity. All right. Well, I also know that let me write this one more step here, and then I'll explain it. I also know from my previous discussions of marginal probability density functions that I can get my marginal cumulative distribution function by doing an indefinite integral on my marginal probability density function. So these things are all equal to one another. These things are all equal to one another. Interestingly, if I have two integrals that are equal to one another, then the integrands have to also be equal to one another. All right? So, from this sequence of things that are equal, I can make this following statement. My marginal probability density function can be found by integrating from minus infinity to plus infinity my joint PDF. All right? If I take my joint probability density function and I integrate over all possible values for y, from minus infinity to plus infinity in y, then I get back my marginal PDF in x. Okay? And similarly for y, my marginal PDF for y would be an integral from minus infinity to plus infinity, my joint PDF evaluated against all values in x. Okay? All right. And I guess a fourth property would be, I guess we call this a property. All right. If I want to know the probability that x lies within a certain range and simultaneously, remember that comma means an and y lies within another range, this is simply a definite integral from x1 to x2, y1 to y2, that. Okay? All right, so let's go back to our example earlier. Let's assume that my joint PDF is my joint exponential PDF that we calculated on a couple of slides back, e to the minus x plus y u of x y. And I want to find the probability that x lies between minus 10 and 2, and simultaneously y lies between 3 and 5. That's what I want to find. All right. Well, very simply, I calculate this integral. Integral from minus 10 to 2, integral from 3 to 5, e to the minus x plus y u x y dx dy. I can get rid of my step function. I can get rid of that step function by letting my lower limit on x be 0. My joint probability density function doesn't exist for x less than 0. And that gives me integral from 0 to 2, integral 3 to 5, e to the minus x plus y dx dy. That's minus e to the minus x evaluated from 0 to 2. All that times negative e to the minus y evaluated from 3 to 5, and you can do the math from here. You can evaluate those exponentials. And lo and behold, my result is 0.0372. 3.72%, just like it was when I calculated this from the original joint cumulative distribution function. So, good for us. All right? All righty. Well, that's all I've got for today. That's my introduction to joint random variables, in particular joint CDFs and PDFs. As usual, if you have any questions, please contact me at your earliest convenience, and I will answer all questions as fully as I am able. Have a nice day. Bye-bye.